Hello everyone, hope you are all doing fine. Welcome back to another lecture on electrostatics. In the previous lecture on electrostatics, we have learned about an electric dipole. We have defined the electric dipole moment as well. And we have also derived the equation for the electric field intensity on the axial and equatorial line of an electric dipole. Okay. In this video, we are going to learn about torque acting on a dipole, which is placed in uniform electric field in detail. Okay. So yes, my name is Vijay Krishna and you're watching Up Phys channel. Let's get started. So what are we going to learn in this lecture? The torque acting on a dipole, that too placed in electric field, uniform electric field. Okay. Uniform electric field. Okay. So we are going to find the torque acting on a dipole which is placed in uniform electric field. Now, so before diving deep into this torque acting on a uniform dipole in a uniform electric field, we have to recollect what we have learned so far about torque, about dipole moment, about uniform electric field. Okay, how does this uniform electric field looks? So it looks like uniform electric field is always represented as arrows with equal spacing. So this is the uniform electric field that we have considered. In this electric field, we have to place an electric dipole, and we know what is a dipole, electric dipole. An electric dipole consists of two equal amount of charges of opposite polarity separated by small amount of distance. So the dipole that I am representing here is something like this. Okay, now here we have minus q charge and here we have plus q charge. Two equal amount of charges, equal magnitude of charges separated by small amount of distance. Two equal charges of opposite polarity separated by small distance. The distance that I am considering it as 2l, as we have taken in the earlier lecture as well. Okay, so minus q plus q separated by small distance 2l. Now this dipole, this is a dipole, right? Dipole we have understood. Uniform electric field also we have understood so far. Now what is dipole moment? Dipole moment. What is dipole moment? Dipole moment. Okay, dipole moment is usually represented with P. It is a vector quantity. This dipole moment P is equal to Q into 2L. Q into 2L. That means magnitude of one of the charges in the dipole into the separation between the two charges. This also we have learned in the earlier lecture. Now, what is torque? What is torque? Torque is the force that causes the rotation. Okay, now how do we represent this torque? Torque tau is equal to force into perpendicular distance to the force from the axis of rotation, okay, and we sometimes write it as fr cos theta, fr sin theta, fr sin theta, because this torque is a vector quantity which is always represented as r cross f, where r is the position vector of force from the axis of rotation and f is the force vector. Okay, now torque is the cause of rotation, especially torque is more often represented as the cause of rotation. Okay, when we apply force, the objects move. Similarly, when we apply torque, when there is torque, then the objects rotate. Okay, the simplest way of explaining this torque. Torque is equal to force into perpendicular distance of force from the axis of rotation, or fr cos theta, fr sin theta. R is the distance to the force from the axis of rotation, and sin theta is the angle between r vector and f vector. Okay. Now, in vector rotation, torque is equal to r cross f. R is the position vector of force from the axis of rotation. F is the force. Now, where is the force in this diagram? Okay, let us understand the force on this, dipole as well. Now, as we all know, when an electric charge, a point charge, or any kind of specific charge is placed in uniform electric field or an electric field, it experiences the force. It experiences the force. That means the force acting on the dipole that we can determine. Okay. Now force F is equal to force on each charge that I am writing. F is equal to E into Q. E into Q. What is E? E is the electric field. E is the electric field. I am writing it as electric field. Okay. E is the uniform electric field. Q is the charge. Q is the charge. For positive charge, force in the direction of field. In the direction of field. That means whatever the direction of electric field is there, in the same direction the force also acting on the positive charge. What if the charge is negative? Q positive, Q negative. Then the force in the direction, in the opposite direction, in the opposite direction of field. By looking at these 2 points, we can conclude that the force on this plus Q is in this direction, E Q. Okay. Now the force on this minus Q will be in this direction, E Q again. Hope my point is clear. Right? There are two forces which are of equal magnitude acting in opposite directions, and these two forces are acting at two different locations. As you can see. Okay. Now, okay. So these are the basic components, basic definitions, basic formulas, basic physical quantities that are required to clearly understand the torque acting on the dipole, to analyze the torque acting on the dipole, to derive the equation for the torque acting on the dipole which is placed in uniform electric field. Okay, I'm going to take everything off. I'm going to keep the important points here. Okay, right. Okay, now force F is equal to EQ, torque tau is equal to RF sin theta, RF sin theta, or R is, tau is equal to R cross F, or dipole moment P is equal to Q into 2N, Q into 2N. Okay, right? Okay, now, or I'm writing it as R perpendicular into F, R perpendicular into F. Now, let us assume the dipole moment Q into 2L. Let us identify the direction of dipole moment. Dipole moment direction will always be from negative charge to positive charge. That means the direction of dipole moment will be this one. P will be P. It will be P. So I am writing it here, P. Okay. So this is the dipole moment direction. Now the electric field direction is this one, to the right. Okay. Let the angle between dipole moment and electric field is theta. Dipole moment and electric field is theta. Now I've taken the dipole at certain angle to the electric field, Okay, right. Now the torque. Let us find the torque. Okay. Now torque. As we all know, torque is R perpendicular into F, or RF sin theta. You can use any of the two. Now let us find. I'm using this one. You can use this one as well. Okay. Now what is R? Where is the axis of rotation? It is here. It is here only, right? Axis of rotation exactly between the middle of the dipole, right? So if the axis of rotation is here, what will be this length? It is L. And what about this length? It is again L. Is my point clear? right? So about this point it is rotating. How is it rotating? This force is pulling this charge in this direction, this force is pulling this charge in this direction, to the left and to the right. Now what happens? This charge will be rotating in this direction, and this charge will be rotating in this direction, like this, like this. Okay, as the rotation is happening, there must be torque, there must be torque. Okay, now torque tau is equal to r perpendicular into f rf sin theta. What is r here? From the axis of rotation to the point, r is, length, r is length. Or if you want to find the r perpendicular, then it will be perpendicular distance, this one, r perpendicular, r perpendicular. Now again r perpendicular will be r l sin theta only, right? R perpendicular is equal to l sin theta only. This r perpendicular is nothing but l sin theta. By looking into this right angle triangle, we can say that sin theta is equal to opposite upon hypotenuse. Hypotenuse is l, opposite is r perpendicular, r perpendicular. Now r perpendicular is equal to hypotenuse times sin theta. Same thing that is written over here. So l sin theta, we are getting the same expression as this one, rf sin theta. What is r? It is l, it is l. R is the distance to the force from the axis of rotation into f into sin theta, into sin theta. Is this clear? Right? Now LF sin theta. Okay. Now, right, now we have another force which is also causing the torque. When you look at the torque due to force on positive charge and force on negative charge, both the forces are trying to rotate this dipole in the same direction, that is clockwise, that is clockwise. As torque is a vector quantity, we cannot add the torque directly, rather we add the torque vectorially. As the two torques acting in the same direction, I am adding them vectorially, LF sin theta, and for this also it will be LF sin theta, LF sin theta, because the torque due to this force also acting in the same direction. I'll tell you in which direction it is acting. Let us understand it even further. Torque is a vector. Torque is a vector. We can find the magnitude by RF sin theta. RF sin theta. R is the R is the distance to the point of application of force from the axis of rotation. F is the force. Theta is the angle between position vector R and F. Clear? Now we can find the magnitude by using this one. How do we find the direction of torque? Okay, without using the formula. That is simple. Because torque tau is equal to R cross F, we can use cross product rule, right hand thumb rule, as I can say. Point the fingers in the direction of R, as this is the first vector in the cross product. R vector, L vector, L. In which direction the force is acting? To the right. Curl them towards right. Then the thumb is pointing inwards. That means the torque on this charge, this dipole, due to this force, is into the board, So this is into, first one is into. Now coming to the second force. Now let us identify the force is in this direction, left direction. Now the position vector to this force from the axis of rotation is this one, right? Now point the fingers in the direction of position vector and curl them towards field. Now the thumb is pointing inward direction. As both the torques are pointing in the inward direction, into the board direction, I am adding them. Okay, so LF sin theta and LF sin theta, what will be the result? Tau is equal to 2LF sin theta, 2LF sin theta. And we know F is equal to EQ, F is equal to EQ sin theta, right? Torque tau is equal. I am rewriting this equation for my convenience, for our convenience especially. E, okay, Q into 2L sin theta, Q into 2L sin theta. What is this Q into 2L? Q into 2L is nothing but dipole moment. So I am rewriting this equation as torque tau is equal to P E sin theta. E, this will give the magnitude of the torque acting on a dipole which is placed in uniform electric field. Okay, so this gives the magnitude. Okay, now everything is clear till now. What is P? It is electric dipole. What is E? It is the uniform electric field. P is directed in this direction, electric field is pointed it towards right. Now what is theta? Theta is the angle between P and E. P and E. Understand the components, I mean physical quantities very clearly, so that you can use this equation very easily while we are solving the problems. Okay, so in spite of knowing the parameters, I mean the physical quantities which are involved in the formula, we will not be able to crack any of the problems. Okay, so we have to understand every physical quantity which involves in the formula, so that we can use it further to uh, to solve the questions, to solve the problems. Okay, right. So torque tau is equal to P sin theta. We use this equation to find the magnitude. Now dipole moment is in this direction, electric field is in this direction. This equation can also be written as torque tau is equal to, if I want to write this equation in vector form, torque tau is equal to P vector cross E vector. P vector cross E vector. And yes, you may get doubt, why did we write this P cross E? Why didn't we write E cross P? E cross P. It's because torque is pointed in inward direction, because torque due to this force, torque due to this force, both are pointing into the board direction. That means the resulting torque must point into the phase direction. By looking at this direct diagram, we can simply say that the net torque is into the board or into the plane of paper. But by looking at this equation, how can we say that the net torque is pointing into the plane of paper or into the board? That is where we use this relation. Okay, so P, point the fingers in the direction of P, and curl them towards E, electric field. Curl them towards electric. Now the stretched thumb is again pointing into the plane of paper. That means we have to write torque tau is equal to P cross E. What if I write this torque tau is equal to E cross P? Does it give correct result or wrong result? Let us verify. Point the fingers in the direction of electric field and curl them towards P. Curl them towards P. The net torque is showing outward direction, which is wrong, because the net torque is into the plane of paper or into the board. But now if we use this relation, we are getting the wrong direction, opposite direction. So this is entirely wrong representation of vector form of torque acting on a dipole placed in a uniform electric field. Hope my point is clear, right? So this is entirely wrong. What is correct? Torque tau is equal to P cross E. We use these two formulas for any analysis of electric dipole acting on, the torque acting on electric dipole which is placed in uniform electric field. Hope my explanation is clear to you. Hope the results that we have obtained are absolutely understandable. Okay, right. So this is how we derive the torque acting on a dipole, electric dipole, which is placed in uniform electric field. Okay, I'm going to analyze this equation even further. We are going to derive the further, more, two or three more equations for better understanding. How do we use this equation? What kind of questions they'll ask in the competitive exams? Okay, right. Now let's move ahead. Okay, right. So we have got, I'm going to draw the diagram again. So this is the uniform electric field where we have a dipole minus Q plus Q, force EQ, field E, and force EQ in this direction, right? And dipole moment direction is P. Now this dipole is making an angle theta with the electric field. Dipole moment is making an angle theta with the electric field. This is what we have learned, and beyond that, the torque acting on the dipole is P E sin theta. P sin theta, or if you want to use it in vector notation, P cross E. P cross E. Okay, right. Now till this point we have learned very clearly, and I think all the steps and the explanation is very clearly understandable, right? Okay, let's move ahead. Now what I'm going to do is, I'm going to leave this dipole free. Okay, I've taken this dipole to some angle theta and I'm leaving it free. Then what happens? Then obviously this will rotate in this direction, this will rotate in this direction. To what extent they rotate? Okay, now what happens after some time? After some time, dipole will align in this direction, minus q plus q minus q plus q again and again, because it gains the velocity by the time it comes and align along the electric field, it again moves to this direction, right? Now let us see, the dipole is aligned in this direction and the electric field is pointed in this direction. Electric field, okay, electric field is to the right and the dipole is aligned along the electric field. I'm taking the case of theta is equal to 0 degrees. Theta is equal to 0 degrees. Then what happens? If theta is equal to 0, then torque tau is equal to Pe sine theta, Pe sine 0 degrees. What will be the result? It is 0. That means net torque acting on the electric dipole in the uniform electric field when it is aligned along the electric field. When it is aligned along the electric field is 0. Is 0. That means the net torque is 0. That means it can be in equilibrium. Okay. We will learn about this equilibrium of an electric dipole in the electric field in detail. Let us discuss one more case. Case where theta is equal to 180. Where theta is equal to 180. Let us suppose. So this is electric field and the dipole is aligned minus q plus q. Sorry, this is plus q and this is sorry minus q. This time electric field direction is this one, whereas the dipole direction is this one. In this case, electric field and dipole moment are pointed in opposite direction. That means the angle between the two is 180 degrees. Angle between the two is 180 degrees. Right? Now, let us find the torque. Torque tau is equal to Pe sine theta again. That means Pe sine theta is equal to 180 degrees. Sine 180 is again 0. That means net torque acting on the system is 0. Is 0. Okay. Now, let us recall one more point. What is the force on plus q charge? EQ. What is the force on minus q charge? EQ. Magnitudes are same, EQ and EQ, acting in opposite directions. Magnitudes are same, acting in opposite direction, and these two forces are acting on the same body, dipole, acting on the same body. That means when the two forces acting on the same system, in our case it is dipole, are equal in magnitude but opposite in direction, then the net force on the system must be 0. In this case, what will be the net force? F net must be equal to 0. Remember this point. Whenever there is an electric dipole placed in uniform electric field, then the net force acting on the dipole is always equal to 0. There is no second thought about it. Okay? In which field? In uniform field only. For any other kind of field, non-uniform field, it is not possible. It may not be possible. It may or may not be possible. F net is equal to 0 possible when it's quite possible when the electric dipole is placed in uniform electric field. So as our dipole is placed in uniform electric field, the net force acting on a system is 0. What is the system here? It is the electric dipole. How the net force acting on the system is 0? Because these two forces are equal in magnitude and acting in opposite direction, and the two forces are acting on the same system, that is electric dipole. So the net force on the electric dipole is 0. Okay, and when we look at the results, in both the cases F net is 0. Whatever the case is, F net is 0 because we have placed this electric dipole in the uniform electric field. Okay, and we have come to a conclusion that net torque acting on the system, net force also 0. Net torque acting on the system 0, net force is also 0. That means, can we consider this situation as equilibrium situation? Am I making sense or not? These two states can be considered as equilibrium states of the dipole, right? Because net force acting on the system is 0, net torque acting on the system is also 0. There is no possibility for the rotation, there is no possibility for the translational motion. So I'm considering the whole system is in equilibrium, right? Right? Does it make sense or not? It is completely making sense, right? Because the net force acting on the system is 0, it is in translational equilibrium, and the net torque acting on the system is 0. That means it is also in rotational equilibrium. So obviously the system is in equilibrium. Whenever we come to a situation to identify the equilibrium, we come to a situation where the system is in equilibrium, then we will get a question whether the equilibrium position is stable or unstable. Stable or unstable. If it is unstable, then we won't have much questions to ask, because it is an unstable state, so we will not be able to analyze in a much easier manner, right? Whenever we come to a conclusion like the equilibrium state is stable state, the equilibrium state is stable, then we can apply that concept to simple harmonic motion. Simple harmonic motion, because whenever we have the situation of stable equilibrium, we can directly take that stable equilibrium concept and apply it to SHM. Okay, right. Let us identify which among the two is stable and which among the two is unstable. Okay, first let us recall what is stable equilibrium. Stable equilibrium is something, stable equilibrium is a kind of equilibrium where when we displace the body slightly, then if that body tries to comes to its original position, its equilibrium position again, if it tries to comes to its original position, equilibrium position again, then we say that equilibrium is stable equilibrium. That equilibrium is stable equilibrium. It is something that we might have learned, that the stable equilibrium concept of a spring. Let us take a spring, let us attach a body and slowly lower it. At some point it will be in equilibrium. Now let us identify whether the position of the object is in stable equilibrium or not. Let us say I've taken that equilibrium body which is in equilibrium, I've used that body and I've displaced that body slightly down or up. Then I removed the, and then I left it free. Okay, then what happens? It moves up and down, it makes oscillations about the mean position, which are a simple harmonic motion, Similar concept will happen here. For example, this is the stable equilibrium. This is the stable equilibrium position aligned in this direction. Now what I am going to do is, I am going to turn this dipole a little bit, slightly displaced. Then what happens? It tries to come to its equilibrium position again, because force is trying to rotate this, create certain amount of torque. The torque is rotating this dipole, right? That means this dipole will come and align in the same direction like this. It is trying to come to its equilibrium position again when I displace it slightly. That means this equilibrium is a stable equilibrium. Hope my explanation is clear to you. It is a stable. Now let us look at this case. Now what I am going to do is, because let me draw this diagram. I've drawn the dipole here, and this force EQ is acting, this force EQ is acting. Now again these two will rotate the dipole in the clockwise direction only. That means the torque is trying to bring this dipole and to align in the direction of field. Due to gain in velocity, it will move like this. It will oscillate, right? That means SHM, it will do, it's a stable equilibrium because it is trying to come to its equilibrium position. Now coming to this one. Now let us say I've displaced this plus Q here, minus Q here, slightly displaced. Then what happens? The force on this plus q will be in this direction, force on the minus q will be in this direction. E q, E q. Then what happens? It will rotate in this direction, this will rotate in this direction. That means it will not come back, it will not come, rather it is continuing its rotational motion, rather it will be continuing its rotational motion. That means this is unstable equilibrium. This is unstable equilibrium. Unstable equilibrium. Hope my explanation is clear, right? If I displace this dipole slightly, then it is trying to come to its equilibrium. It may not be stopping here. It is making oscillations about the mean position, because this is the equilibrium position, mean position. So it is making oscillations, stable equilibrium. When I displace this dipole slightly, it is not coming back, rather it is continuing its rotational motion in the required direction, right? So it is an unstable equilibrium. We don't have much application on this unstable equilibrium, but we have few applications, few special cases on this stable equilibrium. As I have already told you, when we come across a situation of stable equilibrium, we use that concept and we apply that concept to simple harmonic motion. We use that concept in simple harmonic motion. Now let's use that. Let's use this concept of equilibrium of dipole placed in uniform electric field and apply it to SH. Apply it to SH. Okay. Hope my explanation is clear, right? Now, for example, this is the electric field that I have taken, uniform electric field. Okay, uniform electric field, and in this electric field there is a dipole like this. Okay, minus q plus q, minus q plus q. Now, minus q plus q. Now what I am going to do is, it is aligned along the electric field, so it is in stable equilibrium. Stable equilibrium. Now what I am going to do is, I am going to displace this dipole slightly, plus q minus q, plus q minus q. Slightly displaced, to an angle theta, to an angle theta, to an angle small angle theta, small angle theta. Here theta is very small, very small, slightly displaced. Okay. Now the dipole moment is in this direction, so P, and electric field is in this direction, E. The angle between P and E is theta. Angle between P and E is theta. Torque due to electric field is P E sin theta. P E sin theta. Okay. Now this is the torque which is trying to bring the dipole to its equilibrium position, So as it is trying to bring the dipole to its equilibrium position, I can consider this form of torque as a restoring torque, because it is trying to restore the dipole towards into the equilibrium position, right? So that's why I can treat this form of torque as a restoring torque, as restoring torque. Hope my point is clear to you, right? Now let us understand. I was the person who took this dipole and turned this dipole slightly, displaced this dipole slightly. That means there is a torque that I have created. There is a torque that I have created. The torque that I have created, minimum torque that I have created, is torque tau is equal to I into alpha. I into alpha, where I is moment of inertia, and alpha is angular acceleration. So this is the torque that I have created. This is the torque that the electric field is trying to bring this dipole and align in the direction of electric field, to bring it to equilibrium, so restore it to equilibrium. That's why I have treated this torque as restoring torque. This is the torque that is the external torque. Okay, now in equilibrium condition, equilibrium condition in equilibrium condition, applied torque sorry applied torque applied torque must be equal to restoring torque, right? Applied torque must be equal to restoring torque. I'm directly writing applied torque is I alpha, restoring torque is PE sin theta. PE sin theta. I've taken the magnitude. Sometimes I may consider the negative sign also, because it is a restoring torque. It is a restoring torque. If you are asked to find, the angular acceleration, alpha is equal to Pe sin theta by I. P sin theta by I. What is I? Moment of inertia. How do you find this moment of inertia? These two particles having charges plus q and minus q and masses m and m, let it be. Now what is moment of inertia? This is L, this is also L. What is moment of inertia about the axis of rotation? Which is I is equal to, in our case, not every time they may ask you with the same details. Okay, so I is equal to point masses m. So one mass moment of inertia is ml square, and the other mass moment of inertia is again ml square. So I'm directly writing 2ml square. 2ml square is the moment of inertia of the given system dipole. So if I replace this one here, what am I getting? P E sin theta upon 2ml square. 2ml square. So this is how we find the angular acceleration of the dipole in the uniform electric field. You can even extend this question. Okay, you can even apply this concept to conservation of energy as well. That also I am going to do. Okay, and you can apply this concept to SHM as well. Till here we have determined. There will be two more steps to conclude, to find the time period as well. Okay, let us apply this concept to SHM, because the system is in stable equilibrium. If I displace this dipole slightly, then it will make oscillations about equilibrium position, and those oscillations are simple harmonic oscillations. And what is the condition for simple harmonic oscillation? Acceleration A is equal to minus omega square x for translational acceleration. For rotational acceleration, it is alpha is equal to minus omega square theta, where x is linear displacement, theta is angular displacement. So to find this time period of oscillations of electric dipole. Let us find the equation for the time period angular acceleration altogether. Okay, now as I know, alpha is equal to minus omega square theta. Alpha is equal to minus omega. What is omega here? Omega is angular speed or velocity. Angular speed or velocity. Theta is the angular displacement. And we have alpha is equal to Pe sin theta upon I. I'm keeping the moment of inertia as it is, so that you can use this formula directly. You may be given with different masses, different lengths, so that you can use those. Instead of giving the point masses, they may give you a solid sphere. Okay, for that purpose you are going to write the moment of inertia as, for solid sphere it is 2 by 5 mr square. 2 by 5 mr square plus mr square. Okay, that is how you need to find moment of inertia of one object. The other object is also there, into 2. So moment of inertia P sin theta. And we already discussed about the point theta is very small. I displaced the dipole slightly. Okay, slightly displaced. That means theta is very small. If theta is very small, sin theta is identical equal to theta, because theta is very small. If sin theta is equal to theta, then alpha is equal to PE by I into theta. PE by I into theta. As I've already told you, this is the restoring torque. I can take this restoring torque as a negative. But as I am using this concept, including this concept into simple harmonic motion, I am going with negative sign. Otherwise, it is not necessary because magnitudes are enough to solve the questions. But as I am moving into SHM, this negative sign is mandatory, or else you can use the magnitudes. You can use the magnitudes here. Either you can go with taking negative sign here, or you can use magnitudes. Use magnitudes from here. You can do any of the two. Okay, I'm using the magnitude. That would be fine, because instead of placing negative sign everywhere, I can use the magnitude directly. Okay, right. So torque tau is alpha is equal to PE by theta, PE by I into theta. I can magnitude as I have used. So I can equate these two results. Now what happens? Omega square theta is equal to PE by I into theta. Now theta will get cancelled. Okay, you can use negative sign as well, because you will get negative sign on both sides. I haven't used the negative sign here because magnitudes were enough to obtain this equation, but instead I'm using the magnitudes from here. So omega square theta, P by I theta. Theta get cancelled. Omega is equal to Pe by I under root angular velocity. Angular velocity. And recall that the angular velocity omega is equal to 2 pi by time period. 2 pi by time period. So if I replace this 2 pi by t in place of omega here, I will be getting the expression for the time period. So omega is equal from here 2 pi by time period is equal to root over Pe by theta. Pe by theta, right? Sorry, Pe by theta. It's not Pe by theta. Pe by I. It's a Pe by I, right? Pe by I. Now to write this equation for time period, t is equal to, reciprocal it, 2 pi root over I by Pe. I hope I got the correct result. T is equal to 2 pi root over I by Pe, right? So this is the expression for the omega. Did I make anything mistake? Pe sin theta by I, Pe sin theta by 2ml square, Pe sin theta by I, Pe by I theta, right? Omega square theta is equal to Pe by I theta. Omega is equal to, right? We have got the correct results. So T is equal to 2 pi root over I by P. We know what is I, we know what is P, what is E. P is the uniform electric field intensity, P is the dipole moment, where I is the moment of inertia. Okay, so this is the final expression for the time period of the oscillations made by simple harmonic oscillations made by the dipole in the uniform electric field. Okay, so this is the expression for the time period, and we're left with one more case. If theta is equal to 90 degrees, if theta is equal to 90 degrees, then what happens? Torque tau is equal to Pe sin theta, where Pe sin theta is nothing but sin 90. Sin 90 will give you maximum value, which is 1. So torque will be maximum. So to obtain the maximum torque, what would be the angle? What should be the angle between dipole moment and electric field? It should be 90 degrees. Then only we will obtain the maximum torque on the dipole. So I'm going to show it in the diagram as well. Okay. So this is the electric field direction, and this is the dipole direction, minus q plus q, or plus q minus q. However, the direction of dipole moment is this one, and the direction of electric field is this one. Theta is equal to 90 degrees. In such case, the rotation effect will be maximum. The torque will be maximum. Torque will be maximum. I hope the entire concept is clearly understandable. If you still feel difficulty in understanding, please watch it again and comment below if you feeling difficulty in understanding. Okay? So, yes, okay. I hope the lecture is helpful to you. Okay? If you find the lecture is helpful, please like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications. So that's it in this video. Thank you for watching. See you in the